This lesson is for section 8.3. We're going to be simplifying radicals today. Now our objective here actually groups a bunch of different operations together, but we're going to add, subtract, multiply, and divide radical expressions. And we're also going to work on another skill, which is to rationalize radical expressions. Now you might have seen that in Algebra 1 or even geometry, but now we're going to take it a little step further here by asking you to simplify and rationalize nth roots. So in this course we've been simplifying square roots, and now we're going to simplify things like the nth root. So an nth root is of this form here, okay? We've worked with cube roots before. We've even worked with, I think, fourth roots before. So something like the fifth root would look like that, okay? So the 72nd root would look like this. Now, you know, when you see square root, you're missing that little 2, but it's kind of assumed that we have that invisible 2 right there. Now, when you simplify a square root, like for example here in number 1, when you look to simplify the square root of 48, I know some of you guys have different methods, like some of you might want to break that up into the factor tree here, but I wouldn't recommend doing that because it takes a long time. That's also not going to be very helpful when you try to simplify something like the cube root of 72. Now, when you simplify the square root of 48, you're supposed to look for the largest perfect square that will fit inside of 48. So you want to divide 48 evenly by using something from this list here of perfect squares. Now perfect squares are numbers like 1, 4, 9, 16, 25, 36, 49, 64. That number keeps going forever, right? I don't have these numbers memorized. What I'm doing in my head is just thinking 1 squared, 2 squared, 3 squared, 4 squared. That's how I come up with these integers here that are perfect squares. So you don't have to memorize this list either, but what you want to do though is find a number from that list that will divide this number. So when I look at 48, 48 is about right here. So obviously nothing higher in this list will fit inside of 48. So I'm looking for any values here. Now, of course, 4 does fit. It's just not the largest. So when I simplify that and I try to use 4, I'll have to continue to simplify that radical, that root 12 here. If I just look for the largest one in this list, so if I just start from the top and then work my way down, I end up with 16, which is the number I want to use, because now I only have one step. The square root of 48 is the same as root 16 times root 3, which simplifies to 4 root 3. Okay, so I know that this is mostly review for you guys, but that same concept is now going to be applied to when we try to simplify a cube root. So for a cube root, we're looking for cubes. Now our list of cubes can be found by taking 1 cubed, 2 cubed, 3 cubed, 4 cubed. So I'm not as fast, you know, listing these out loud, but all I have to do is think of 1 cubed, which is 1, 2 cubed, which is 8, 3 cubed, 27, 4 cubed is 64, 5 cubed is 125, and so on. So now when I look at 72, I want to look in this list here and see what divides that. So even though our list of cubes can continue forever and forever, right? If I just found additional values like 6 cubed and 7 cubed, we can narrow this down because 72 is going to fall between 64 and 125. So clearly we can't look higher than 64 since we're trying to divide it into an integer value here. So I'm going to look at 1, 8, 27, and 64 to see if it divides 72. Now the only number that does that is 8, right? 8 divides 72 evenly. So I can rewrite the cube root of 72 as the cube root of 8 times the cube root of 9. Now the cube root of 8 is helpful to me because I can simplify that and reduce that to just an integer value 2, right? The cube root of 8 is 2, so now I have 2 times the cube root of 9. This is the simplified radical expression for your original cube root of 72. Now some of you guys are going to try to revert back to what we've done with square roots. You're going to think to yourself, oh, 36 fits inside of 72. So you're going to break that up into the cube root of 36 times the cube root of 2. But this value, if you try to rewrite that as 6, what you're saying then is 6 times 6 times 6 is equal to 36. That's really what a cube root is saying. What times itself 3 times will give you the value inside? Well, clearly that's not the case, right? 6 times 6 times 6 is not 36, so that can't simplify here to 6, which means it doesn't help us to rewrite it in that way. You have to look at your list of cubes when you want to simplify a cube root. Okay, now in number 3, we're really increasing the difficulty here when we try to simplify these square roots. Now, to add or subtract square roots, you have to make sure you follow some rules, and now I want to just review them really quick with you. If you want to subtract or add 2 radical expressions, they have to be the exact same radical. So for example here, root 5 plus root 5 would give me 2 root 5, or even 3 root 5 plus 2 root 5, that would give me 5 root 5, okay? I can add those just like I can add 3x plus 2x. Think of this as a variable expression, even though it's not really a variable. Think of it like that in terms of like terms. You can add these two. However, if we saw something like 3 root 5 plus 2 root 2, we cannot simplify that at all. That's like seeing 3x plus 2y, right? Completely different radical expressions. So we can't simplify that. We'd have to leave it as 3 root 5 plus 2 root 2, just like you would have to leave 3x plus 2y as 3x plus 2y, okay? Now in this problem, this can look really intimidating when we try to simplify this because we have such large numbers here, okay? My advice to you is to make sure you look at the smallest radical first and try to simplify. Now root 20 on its own is pretty easy to simplify. I can rewrite negative 8 times the square root of 20 as negative 8 times the square root of 4 times the square root of 5 because 4 is the largest perfect square that fits inside of 20. All right, now if I do that, I'm going to simplify that to 8 times 2, so negative 16 root 5. Okay, this is giving me a hint because if I want to add or even subtract this value, right, from something else, I need to have the same radical expression. So my guess now is that in the other radicals, I can probably divide those by a 5. So if I try to divide 125 by 5, I end up with the square root of 25 times root 5, right? Those two multiply to give me 125. And this is really helpful because the square root of 25 is just 5. So now I have 4 times 5 times root 5 minus 16 root 5. Then if I divide the 5 here, I'm going to end up with, let's do this really quick. Can't believe my mental math is so bad. I'll get 36 here. Okay, so I have plus 2 times the square root of 36 times the square root of 5. Now again, this is really helpful because that's going to simplify to just 6. So right now, let's just simplify so far what we have. 4 times 5 gives me 20. So I have 20 root 5 minus 16 root 5 plus 2 times 6, which is 12 root 5. And then from here, I just look at, I guess you can call them coefficients. Even though they're not technically coefficients, we'll just look at the numbers in front of those radicals. So we have 20 minus 16. 4 plus 12 gives me 16. So I have 16 square root 5. Okay, so that's the simplified expression for this original radical expression up here. All right, now in number 4, we're trying to simplify some cube roots. We want to add and subtract different cube roots. Now the same strategy applies here as we worked on in number 3. We want to look at the smallest cube root first and try to simplify that because then that might help us to simplify the other remaining ones. So when I look at 2 times the cube root of 48, rather than trying to split that up into something like the cube root of 16 times the cube root of 3, I don't want to use a perfect square, right? I want to look at my list of perfect cubes because this value, the cube root of 16, does not reduce to something nice, right? The cube root of 16 is not something I can simplify. So instead, I look at numbers like 1, 8, 27, 64, and so on, right? 1 cubed, 2 cubed, 3 cubed, 4 cubed, and so on, okay? Now in this case, the only one of these numbers here on our list that will divide 48, that's not bigger than 48, so I have to look, you know, at these numbers here, 1, 8, or 27, will be the number 8. So I can simplify that, 2 times the cube root of 8 times the cube root of 6, okay? So now when I simplify this, I end up with 2 times the cube root of 8 is 2. Now the cube root of 6 is just going to be brought down here because I can't simplify the cube root of 6. Now this is helpful, right? This cube root of 6 is giving me a hint about what I might be able to divide 384 and 750 by. So that's what I'm going to look to do now. I'm going to divide 384 by 6. So here is something where you'd want to use long division. So how many times does 6 fit into 38? 6 times. Bring down, subtract and bring down that 2. Whoops. You have 24 left. So 6 fits into 384 64 times. So we can split this radical up. Okay, so let's rewrite that, I guess, up here. We have the cube root of 6 times the cube root of 64. Now I like to rewrite this so that the one that is going to be able to reduce comes first. So let's just rewrite that as the cube root of 64 first times the cube root of 6. So the one that I know isn't going to simplify, I like to write that one second. Okay. Now I'm going to do the same thing for 750. So I'm going to take 750 and divide that by 6. So let's see, that fits inside 2, 3, 30, 125 times. Okay. Now some of you might be able to do this mentally, which is great, but others are just going to have to use long division. All right, so we have 3. Don't forget that 3 out in front. So 3 times the cube root of 125. I want to write that one first because that actually simplifies and reduces, times the cube root of 6. All right, so let's work on each part. So we already simplified that first expression here. We broke that down. This next expression, The cube root of 64, that's 4. So I have 4 times the cube root of 6. Then I have 3 times the cube root of 125 is 5 times the cube root of 6. Now from here, I'm just going to simplify a little bit further. 2 times 2 is 4, so I have 4 times the cube root of 6 minus 4 times the cube root of 6 plus 15 times the cube root of 6. So clearly here, these two terms will cancel one another out, leaving me with 15 times the cube root of 6. Okay, our next major skill is rationalizing the denominator. I want to make sure that you understand this terminology, so I'm going to explain that real quick. When you see a number like 1 over the square root of 3, right now in the denominator you have an irrational number. Okay, to rationalize this means you want to manipulate it somehow so that instead of seeing a radical, you just see an integer or some value that you can rewrite this entire fraction here as a ratio, a rational number. Okay, so that's what we're actually going to be doing in all of our answers. We don't want to see a radical in the denominator. We want to try to manipulate it so that we don't see that radical. So for example, in number 5 here, I see the square root of 16 over 5. Now whenever you have a fraction, sometimes it's really helpful to rewrite that in terms of two different radicals. So I can actually split this up using a rule. I can split that square root of 16 over 5 into root 16 over root 5. Now the square root of 16 is 4, but the square root of 5 doesn't simplify, so I still have a radical in the denominator. So now my goal is to rationalize this denominator because I don't want to see that radical in my final answer. So what I'm going to do now is multiply by root 5 over root 5. Okay? The reason why I can multiply by root 5 over root 5 is that this value is equal to 1, so I'm not really changing this number at all. But the fact that I'm rewriting it as root 5 over root 5 helps me because in the denominator, root 5 times root 5 is root 25. And we know that the square root of 25 is 5. So all of a sudden that radical drops. Okay, so I've picked specifically root 5 over root 5 because that's the radical in the denominator. Now in the numerators, when we multiply fractions, we just go right across. So the numerator here becomes 4 root 5. So really all I'm doing is applying the value of 1 here. I'm multiplying by 1, but I'm rewriting it as a fraction so I can multiply straight across. Okay, so that becomes 4 root 5 over 5. That's the rationalized expression for this original radical expression here. Now when we try number 6, this is going to be a lot trickier. So in number 6, we want to rationalize 4 over the cube root of 5. Now some of you, after we just rationalize the square root, you're going to want to multiply by cube root of 5 over the cube root of 5. Okay, this is actually not correct. Even though that's actually equal to 1, right, that value here is still just equal to 1, it doesn't help us in trying to rewrite the denominator as just 5. This doesn't actually work. Now the reason why this doesn't work is explained over here in this little bigger picture note. So in this note here, we're trying to explain why the square root of 36 actually equals 6. I know that you've had this memorized forever and you just kind of accept it for what it is, but there's actually some math behind that. Now, the square root of 36 can be rewritten as the square root here with that nth root idea. So let's put that 2 back here on the outside of the radical. Then I can rewrite 36 as 6 squared. Now, when I take the square root of something squared, those are inverses of one another, right? Square root versus squared, those are opposite operations. That's why those opposites cancel each other out, leaving you with just the 6. Okay, so for example, when we worked with the square root of 5 times the square root of 5, really what we're looking at is the square root of 5 squared. So if we have the 2 here and the 2 here, those cancel each other out, which is why we end up with just 5. Now, when we look at a cube root, the cube root of 27 is equal to 3 because we can rewrite 27 as 3 cubed. These are opposite operations of one another, leaving us with just the 3. So just to extrapolate here, if we see the x root of y to the x, these are opposite operations. These are inverses of one another. These are going to cancel, and that will leave me with y. Okay, so tying this back to our problem number 6 here, when we try to rationalize 4 over the cube root of 5, what I want to do is try to get in the denominator the cube root of 5 cubed. If I can get that in the denominator, I know that the cube root of 5 cubed, those will cancel and leave me with just a 5, so I'll get rid of the radical. So I can't just multiply, so let me go back to trying to multiply by the cube root of 5. If I do that, I only end up with the cube root of 5 squared, right? I would just add the exponents here, the 1 and the 1 here, to get the cube root of 5 squared. That clearly doesn't cancel each other out. Those are not inverses of one another, not quite yet. So what I'm going to do is adjust this. Instead of multiplying by the cube root of 5 over the cube root of 5, I'm going to multiply by the cube root of 5 squared over the cube root of 5 squared. Okay, this is the big idea basically for today's lesson. You have to make sure you understand why we're doing this. Now, the fact that I'm multiplying by the cube root of 5 squared means that in the denominator now, I'll have the cube root of 5 cubed. 1 plus 2 5s here gives me 5 cubed. In the numerator, I still have 4 times the cube root of 5 squared. Okay, and that doesn't change at all, so I just multiply across still. Now, in the denominator, this expression here simply reduces to just 5 because these are inverse operations of one another. So now overall, my final answer is 4 times the cube root of 25. I just simplify this 5 squared here. Okay, so 4 times the cube root of 25 over 5 is the rationalized expression for our original problem 4 over the cube root of 5. And I know that's a lot to take in, and we've only done a few problems so far, but this is probably the most important problem that you understand. So then now we can hopefully try to go through the rest of the questions here a little bit quicker. Okay, so in number 7, I'm trying to rationalize 1 over the cube root of 2. Now if I try to multiply this by the cube root of 2 over the cube root of 2, this isn't going to be helpful because I only end up with, in the denominator, the cube root of 2 squared, right? I would just add my exponents when I try to multiply these radicals together, and since these are not inverses of one another, I can't just cancel that out, and I can't just rewrite that as just a 2. So the radical is still there, okay? Some of you will incorrectly try to rewrite that as 2, but that's not equivalent to 2. So instead, we're going to multiply by something a little bit different. We're going to multiply by the cube root of 2 squared over the cube root of 2 squared. So this is still equal to 1, right? That value is equal to 1, so I'm not really changing the problem. I'm still multiplying by 1. But because I'm rewriting that as the cube root of 2 squared over the cube root of 2 squared, in the denominator, I can rewrite that as the cube root of 2 to the third. So I'm just adding again the exponents. So 2 to the first times 2 to the second gives me 2 to the third. Now in the numerator, that's going to stay 1 times the cube root of 2 squared, so I'm just going to simplify that right away, because cube root of 4 I can't change at all. So this is as simplified as that numerator will get. The denominator, though, since these are opposite operations, those are inverses of one another, that will simplify to just 2. So I have the cube root of 4 over 2. This is the simplified and rationalized expression for number 7 here, 1 over the cube root of 2. All right, now in number 8, if you're trying to rationalize this, some of you might be thinking that you should multiply by the 5th root of 4 to the 4th over the 5th root of 4 to the 4th. And it's not that you're wrong, right? Because this would certainly, in the denominator, make that the 5th root of 4 to the 5th, and because they're inverses, that would allow you to rewrite that denominator as just 4, so you're dropping the radical here. The problem is that in the numerator, the 5th root of 4 to the 4th is the same as the 5th root of 256, right? 4 to the 4th is 256. This radical is not simplified. It's like leaving your answer as the square root of 48. So I would take off points here because the square root of 48 is not simplified all the way, just like the 5th root of 256 is not simplified all the way. Now this is really hard for students to see because you're not as familiar with simplifying that as if you were simplifying here, right? Square root of 48, most of you will recognize that you need to simplify that further, but this one, not so much. So instead of multiplying right away by the 5th root of 4 to the 4th over 5th root of 4 to the 4th, I'm going to rewrite this answer, or this denominator here. Okay, so whenever you see a radical, what you want to do is try to rewrite that radical that appears in the denominator using the lowest power here that we can. So I can rewrite 4 as a power of 2. So if I want to rewrite that, I can rewrite that as the 5th root of 2 squared, right? 4 is the same as 2 squared. Now because I'm rewriting it as 2 squared, instead of multiplying it by a 5th root of 4, I'm going to multiply this by a 5th root of 2 cubed. Okay, so the 5th root of 2 cubed. The reason why I'm doing that is because now I can add those exponents, and that'll give me the 5th root of 2 to the 5th. So in the denominator, I now have the 5th root of 2 to the 5th power. In the numerator, I have the 5th root of 2 to the 3rd, which I'll rewrite as 8. Now in the denominator, because I have the 5th roots here, those will cancel and leave me with just the 2 in the denominator, so I've rationalized the denominator. In the numerator, I can't reduce the 5th root of 8 any further. So this is the simplified expression here, as opposed to the original one that we got that was the 5th root of 256 over 4. Okay, so this is not wrong, it's just not simplified all the way. It's like leaving your answer as 8/16 when you can rewrite that as 1/2. So it's just not simplified all the way. So that's why when you come up with a problem in the radical where you can rewrite that as a smaller power, you want to do that. So here I can rewrite that as 2 squared. Okay? Okay, in number 9, I want to rationalize the denominator here, but here I have 2 different radicals in the denominator. Some of you are going to want to get rid of that by multiplying by root 7 over root 7. The problem with this is that when you distribute that term to both parts in the denominator, it only gets rid of the first radical. So I have root 7 times root 7 is 7, but root 7 times root 3 is root 21. So I'll still have that radical here. Now if I try to, so the numerator is 4 root 7, but if I try to get rid of that radical the root 21 here by multiplying by root 21 over root 21, I'll still, after I distribute, end up with a radical here because it only gets rid of these terms, that radical here. So it's kind of a never-ending vicious cycle if you try to get rid of one radical at a time. So what you're going to do instead is you're going to rely on one of these patterns over here. Now hopefully you have all of these memorized. When you take the quantity x minus y and you square it, you're going to get this trinomial here. When you take x plus y and you square it, you're going to get this trinomial here. Notice that you're going to have the twice the product of the two terms, right? 2 times x times y. It just depends on the sign, right? The negative or the positive here. However, when you take x plus y and you multiply it by x minus y, we get that difference of squares pattern. That's what we're going to use here. We're going to pick smarter values to multiply by, because if I multiply by root 7 minus root 3 in that denominator, now I just square the first term and I square the second term and I put a subtraction sign between it. If I square root 7, I get 7. If I square root 3, I get 3. So if I stick a subtraction sign between that just leaves me with the number 4. So I've gotten rid of the radical by multiplying by the conjugate. So I need to multiply by that in the numerator too. Don't forget to do that. So you have root 7 minus root 3 over root 7 minus root 3. So this gives me a nice difference of squares, which will reduce to this, 4. And in the numerator I have 4 times root 7 minus root 3. Now in this case I'm not distributing this. You probably should in most cases, but here, because I have that 4 in the denominator, it's easier to cancel the factors here. These are like factors, which will leave me with just root 7 minus root 3. Okay, so this is that expression when we rationalize it. It's just root 7 minus root 3. All right, now in number 10, we're trying to subtract two fractions. And you've always been taught that when you're trying to subtract fractions, you need a common denominator. The thing is, you have a radical in the denominator for one of the terms. So I would suggest first getting rid of that radical and rationalizing the denominator so you don't have to deal with a radical. Because at the end of your answer, you should always rationalize it anyhow. So I get rid of them first. It reduces the work that I have to do if I just get rid of it right away. So I'm going to multiply that first fraction here by root 6 over root 6. Okay, and then that's going to simplify to 3 root 6 over 2 times 6, which is just 12. So I have 3 root 6 over 12 minus 3 root 6 over 6. So that's the second fraction here. Now, this is much easier to deal with. The common denominator here is going to be 12, so now I have to manipulate that fraction by multiplying by 2 over 2. So I have 3 root 6 over 12 minus 6 root 6 over 12, and that's going to give me negative 3 root 6 over 12. Which will simplify to negative root 6 over 4. Okay, number 11, I'm going to begin by rationalizing this denominator first before I try to add these two terms together. So let's work on that first. Now when you rationalize this, be careful that you don't try to just multiply by the 4th root of 9 over the 4th root of 9, because if you do that, you only get the 4th root of 9 squared. Right? Obviously, these are not inverses of one another, so we're not left with just 9, although some students will skip right to here and write that as 9 in the denominator and they drop the radical, so that would be incorrect. Okay. Now, we also could try to multiply by the 4th root of 9 cubed over the 4th root of 9 cubed, and this is on the right track at least. The problem is, though, that even though these do cancel in the denominator and I'm left with just 9 here, the numerator is 6 times the 4th root of 729. Now this is not simplified, just like something like the square root of 32 is not simplified all the way. This is harder for you to recognize that it's not simplified, so rather than doing the work at the end, you can actually avoid having to simplify really difficult nth root if you look at the original expression here and you try to simplify that right off the bat. So instead what we're going to do is rewrite this denominator here as 6 over the 4th root of 3 squared. Now when I look at that, if you go back to your rational exponent properties, you should be able to recognize this as 3 squared to the 1/4 power, right? We can rewrite that as 3 squared to the 1/4 power, which is the same as 3 to the 1/2 power. And that's the same as the square root of 3. So this entire denominator is equivalent to 6 over square root 3. So now that I've got it written as a square root, now it's a lot easier to try to simplify that. We just multiply by root 3 over root 3. So we end up with 6 root 3 over 3, and that'll simplify to 2 root 3. So just to make sure we go back to our original problem, we're supposed to add that to this other radical here. So we have 2 root 3 plus 2 times the 4th root of 3. Now, just because these both have a 3 inside that radical does not mean these are like radicals. So we can't actually add this This is as simplified as that's going to get because these are not the exact same radical terms, okay? So that's our answer for number 11. Okay, to finish off the lesson, I just want to discuss some of the common errors that we've seen on tests and quizzes. Now, there's definitely the kind of errors where you just make a small mental mistake, you know, you add 2 numbers wrong or something like that. But then there's conceptual errors, and those are a big deal, you know, to us as we grade your tests and quizzes. So I just want to talk about 2 very common conceptual errors. So in this first example, this person has tried to rationalize the denominator, and clearly they don't understand that multiplying by root 2 over root 2 won't clear the denominator of radicals, because if you distribute here, we should end up with 7 root 2 plus 2, not just 7 plus 2. So in this case, what this person should have done is multiply by the conjugate 7 minus root 2 over 7 minus root 2 to create a difference of 2 squares. Okay, so I'd like you guys to try this problem on your own and check with the key to see if you get it right. All right, now in number 2, I'm just trying to highlight again to you that when you try to rationalize 4 over the cube root of 3, you can't just multiply by the cube root of 3 over the cube root of 3, because if we multiply out those denominators here, I end up with the cube root of 3 squared. Now hopefully you're realizing that these are not inverses of one another, so you can't just call that 3. That's not equivalent to just 3 in the denominator, so you haven't really gotten rid of the radical, so this step here is definitely incorrect. Now what I'd like you to do is try to do this problem on your own. It's going to take you about 2 seconds to do anyhow, but check it with a key so that you get practice doing it on your own for once, since I've done all the problems with you. So go ahead, check that one with the key, but that's the end of the lesson. Nice job. See you tomorrow.